Dear fellow scholars, in this video, we present our work on neural refinement for absolute pose regression with feature synthesis. Absolute pose regression or APR methods directly regress the camera pose with a single forward pass of a neural network. However, because of lacking explicit 3D priors, recent work has shown that APR approaches have trouble generalizing beyond their training data. They are also significantly less accurate than state-of-the-art geometry-based methods. To address these limitations, we propose a novel test time refinement pipeline that integrates implicit geometric constraints using a robust neural feature field. Our method enhances APR's ability to utilize 3D information during inference, significantly improving accuracy. Our pipeline consists of three main components. First, a pre-trained APR network that provides an initial coarse pose estimate for the input image. Second, the neural feature synthesizer that renders a dense feature map from the coarse pose. And third, a feature extractor that extracts dense features from the query image. Here is a high-level illustration of our test time refinement process. During refinement, we compute the feature metric error between the rendered feature map and the query image features. This error is minimized iteratively, refining either the APR network parameters or the coarse pose directly. Central to our approach is the neural feature synthesizer, or NFS, which directly encodes 3D geometric features during training and renders dense novel view features at test time to refine APR methods. NFS combines an implicit representation-based geometric refinement with an end-to-end learning framework, allowing gradients to be backpropagated to the APR network during test time. To ensure robustness, we introduce two key components. First is the exposure adaptive affine color transformation that compensates exposure differences between images by adapting the color output based on the query image's histogram. This enables NFS model to render the correct exposure of the query image during inference. And second is the feature fusion module that fuses rendered colors and features, producing a final robust feature map for refinement. We propose a progressive training strategy to train NFS. We first initialize NFS with photometric loss to learn reasonable geometry. We then enable feature loss for neural feature distillation. And finally, we train the feature fusion module that fuses rendered colors and features to produce optimal features for test time refinement. Here we can see a visualization of the pose refinement using APR method and using our NFS model. As we can see, NFS leads to a much accurate pose as compared to the APR estimated pose. We can also see some qualitative comparisons of different APR methods with and without NFS. Here is PoseNet and PoseNet plus NFS. Here's MS Transformer with NFS, and DFNet with NFS. Quantitatively, our method outperforms all of the state-of-the-art APR methods on both translational and rotational errors. We see this on both outdoor and indoor datasets. We also note that we can optimize both APR weights or we can optimize the poses directly. And our refinement method works on different APR architectures without further training. Thank you for watching. You can visit our project website or scan this QR code for more details on our project, and you can read the article there. Thank you.